quantitative Neumann lemma for finitely generated groups. This is joined with Elia, who's an undergrad at Caltech and is going to be a grad student to be determined where next year, and Nicolás. Okay, so let me start with a very basic and simple question. I'm going to look at z squared, and I'm going to look at infinite index subgroups of z squared. So what are the infinite index subgroups of z squared? Well, there's a trivial one, which is just the identity. And then there are these sort of things that are one-dimensional. For example, this sort of thing. So, you know, and I could take every other element here that would also be an infinite index subgroup. And then I'm going to look at cosets of infinite index subgroups, which means I take this and I shift it. So, you know, maybe to, I guess I shouldn't close this off. It continues, and a coset of this subgroup is something like this, right? What things? And here's another coset of an infinite index subgroup. This, right? So all of these are cosets of maybe different infinite index subgroups of z squared. And what I want to do is I want to cover the ball of radius r with cosets of infinite index subgroups. And the question is, how many such cosets of infinite index subgroups, which I'll call CII. So CII is a coset of an infinite index subgroup. How many such cosets in z squared do I need to cover the ball of radius r? So what's the answer? Sorry?
2r.
Yeah, maybe
No,
2.
R. Sorry.
R, no, I think maybe it is 2r plus 1.
It's the same subgroup.
Sorry?
Do you fix a subgroup and look at cosets of that subgroup, or do you like?
No, I allow like in this picture cosets of different subgroups. Okay, and you know, I also didn't tell you exactly what is the ball of radius r, but maybe it's. But the point is, it's something order of r. Maybe r plus times 2 plus 1, or okay. Why is that? If we take just one subgroup and look at all of its cosets, then then it's obvious that I'm going to need something like 2r of them to cover it. But if I'm allowed to use different cosets, why is it that I can't do any better? Well, the intersection of any such coset with the ball of radius r contains at most r or 2r, or a linear number of elements, and there's something of order r squared elements in the ball, so I'm going to need at least r of these cosets to cover the group. So far, so good? Okay, and you can imagine in z cubed, I get the same answer. So here I have one-dimensional subgroups, but they're not going to be so interesting because I can go bigger. I can have these two-dimensional subgroups. How many two-dimensional, cosets like this am I going to need to cover the ball of radius r? By the same argument, it's again something like r. Okay, so in ZD, I'm going to write it like this. C of r is something like r. And C of r is the minimum, I'll define it formally in a second, is the minimum number of cosets of infinite index that I need to cover the ball of radius r. And the question is, what happens more generally for finitely generated groups? So let me write down the formal definition. So I'm going to let G be generated by a finite, say symmetric S subset of G. And I'm going to denote by BR, and maybe if I want to be specific, BR of GS, the ball of radius R. C equals HG, I'll do it from this side, is a coset of infinite index if the index of H and G, and I'm going to probably get it wrong. Is it like this or the other way around? Maybe the other way around. No, I'll write it like this. If H mod G is infinite.
It's G mod and G mod.
It's G mod H, good. No, but I want on the other side, like this.
Yeah.
Okay, good. And I'm going to define C, and maybe I want to say specifically CGS of R is the minimum of the set of all n, such that there exists CIIs C1 up to Cn, such that the ball of radius r is contained in the union of these CIs. Okay, so in words, what I said before, C of R tells you how many cosets of infinite index subgroups of perhaps different infinite index subgroups do I need to cover the ball of radius R. So far, so good. Any thoughts, questions, comments, guesses? Oh, I can use this. So we know the answer for ZD. And now you can ask, okay, maybe there's a very, very strange group where actually I need just finitely many cosets to cover the entire group. Okay, and the answer is no. So there's a lemma proved by Neumann in 1954 that says G is not equal to C1 union C2 union so on union Cn for cosets of infinite index C1 up to Cn. Okay, so take any group, take any finite number of cosets of infinite index, they're not going to cover the entire group. The proof here is completely sort of algebraic. There's a very nice intuition for this in the amenable case. So here's how you prove this in the amenable case. You do probabilistic proof, but the probabilistic proof is going to use a finitely additive measure. So because the group is amenable, there's a finitely additive measure that is invariant to translations. So this measure, if this is my group, and this is a subgroup H, I have a measure that's invariant to translations. It's going to assign the same measure, probability measure. It's going to assign the same measure to all cosets, but there are infinitely many of them, so it has to assign 0 measure to each one of these cosets if the H is of infinite index, which means that the measure that it assigns to this finite union is again 0. So you get that the total mass of in an amenable group of this finite union is again 0 for any invariant measure. Okay, for non-amenable groups, we don't have invariant measures like this, finitely additive, so this argument doesn't work, but the lemma is still right. In fact, that you'll see what we're going to do is sort of related to this kind of argument, but we'll do it more generally for any groups. It's sort of probabilistic argument. One way of thinking about this is I'm going to choose a point in the group at random uniformly from this finitely additive measure. And with probability 1, I don't choose something that's inside this union, right? So if you want to have a sort of probabilistic thinking about these finitely additive measures, whatever that means that if I throw a dart at the group and it hits things uniformly in the sense that they're invariant, then the probability that I hit this union is in fact 0, which means in particular it's not equal to the whole group. Okay. Good.
So in non-amenable case, the proof is still probabilistic.
So his proof for the general case is not probabilistic. It's algebraic, and he looks at this and that. There is a version of you can do a sort of probabilistic proof. In fact, I'll do one that will even give this a little bit more. So you'll see the. Good. So this says something very basic. It says I can't cover the entire group with just finitely many. it doesn't immediately imply that this C is not bounded, because you could imagine that for different radii, I can always do it with 17 cosets. I can always cover, for any radius r, I can cover with 17 cosets of infinite index, but maybe I need different ones for different radii. So this doesn't imply that it's unbounded, but okay, we'll see that it's in fact unbounded. But what can we say generally about this C? So I think a very natural and intuition is that just like in ZD, I'm going to need R. Or maybe I'm going to need at least R. Maybe for some weird groups, I'm going to need more than R. And this question is actually open, so I don't know how to prove that. Okay, that you need at least R. I do know how to show that for some groups, you need more than R to cover the ball of radius R, but I don't know how to show that R is enough for any group. So I'll mention this open question again at the end.
But at least R is clear, right? You know that you need at least R for any group.
No.
Oh, okay.
I don't know that I need at least R. So let's ask what happens in the free group. So I'm sure this has been drawn a few times already these 2 weeks. I have the Cayley graph of the free group. I have groups of infinite index here, and groups of infinite index, which means that there's the Schreier graph that's related to it, which I'm not going to define, but hopefully most of you know what that is infinite. I want to cover the ball of radius R with as few cosets of these groups as possible. And the question is, how many do I need in the free group? Okay, so here's a very easy claim. So we're talking now about the free group F2. The number of cosets of infinite index that I need to cover the free group of with two generators, most R. So I can do it with R. Maybe less is enough, but I can do it with R. Why is that? Well, the idea is I have a quotient to Z squared. Since I can do it in Z squared, I can pull back these cosets of infinite index through this quotient back up to F2. And they're going to be cosets of infinite index in F2. Now, the ball of radius R in Z squared, I can pull that back also, and that's going to contain the ball of radius R in F2. So let me write that down formally. So this is a claim. Here's the proof, or proof very quickly written. We're going to look at a quotient from F2. In fact, we can just look at a quotient to Z. How do I cover Z with a linear number of cosets of infinite index? Well, the only infinite index subgroup of Z is the identity. The cosets are just singletons. So I just take, union of two are singletons. So I have this quotient to Z. And I'm going to take C1 up to Cn, covering the ball of radius R in Z, which I can just take these to be singletons. Then pi inverse of Ci is a coset of infinite index in F2. And pi inverse of the ball of radius R in Z contains the ball of radius R in F2. So we're done. We're just going to cover it with these things. Okay, so more generally, whenever I have a quotient to something, if I can cover that quotient with some number of cosets, I can cover the original group with that number of cosets. And by the way, when I say R here, I always mean up to constants, right? So this is all going to be order of. We're going to wonder if things are linear, quadratic, exponential, whatever it is. And also the choice of generating set, which I dropped here, is also, again, only going to matter up to constants. And another thing which takes a little bit of annoying work to prove is that finite index subgroups are always going to have the same answer again up to constants. Okay. But what we have here is that if I have a quotient that I can cover with some number of cosets, I can pull that back up and cover the original group with some number of cosets. But because F2 has quotients to everything, well, generated by two elements, F2 is the worst case. If I can cover anything with, say, log n cosets, then I can cover log r coset, right? If I can cover the ball of any group of radius r with, say, log r coset, I can also do it for the free group, right? So if so the free group is a very interesting case because it's in some cases the hardest case. Now I have quotients to all groups generated by two things, but the free group has inside it, as a finite index subgroup, free groups of all finite orders. So in fact, understanding what happens in the free group is the same as understanding what happens on any group, at least one side of it. So if I can do something, the lower bound, okay, anyway, one side of it, because the free group is the worst case for all groups. Okay.
You get the best upper bound.
Up to sign of bounds and worst and best and lower and upper. Yeah. But I hope everybody understands what I'm saying. Up to sign.
So when you're saying you don't know a group where it's less than R, you're just saying you don't know if the free group that it's less than R.
Exactly. Knowing a group, if you could do this for any group, you could do it already on the free group. Okay. So this question, yeah, so we need to understand these infinite index subgroups of the free group. These are not so easy to understand. So the geometry of how these free groups embed in the Cayley graph is not so simple. It's kind of nice to think about them in terms of their Schreier graphs. There, it's very easy to work with, but that's not what we need. We need the other way of thinking about it, which is more difficult, which is why I still have this open question. Okay. And any more thoughts or?
Maybe you'll mention it, but do you have any lower bounds for the free group?
Yes. So this is there was a question of you because that's the next thing we're going to talk about. So I do have a lower bound for the free group, and in fact, it's going to be, because of what we just said, it's going to be a lower bound for any group. Okay, so here's my my first theorem, and this is Elia has a very long last name. I should advertise. I mean, and what the theorem says is this: for any finitely generated group G generated by S is symmetric, the covering number, this coset covering number, the ball of radius R, is at least the square root of R divided by 4 times the size of the generating set. Okay, and this is the best we have for the free group, and which means it's the same as the best lower bound that we have for general. Okay, is the statement of this clear? Okay. So let me show you the proof for this, and the proof of this is where we're actually going to have measured group theory. So far this is maybe group theory, but there's no measured group theory. So now we're going to bring in measured groups just as a proof technique for proving this. We're going to do a probabilistic proof using random walk. And I mean, in some sense, the proof is trivial. These are all, everything else right there is sort of Lego proofs where you just take things done by other people and put them together. There's nothing technically difficult about anything that I'm going to say today. So if I give you that impression, it means that I'm not explaining things well. It should all be our contribution here, at least, is more or less trivial. So good. So how do we prove this? We're going to let mu be the uniform measure on S, and we're going to do a mu random walk. So I'm going to use probabilistic notation here. I'm going to let x1, x2, and so on be random variables that are IID mu, right? So I choose independently from mu. These are going to be the jumps of my random walk. And I'm going to let Zn be the product x1 up to xn. This is what Josh wrote, G, I guess he called these G's. But this is the locations of my random walk. So I have my group with the identity, and I have the ball of radius r, and I'm going to do this random walk, and I'm going to do it for r steps. So I'm going to end up at some point zr, and this point is going to be in the ball of radius r. Why? Because I've taken r steps, so I'm inside. So with probability 1, I'm inside the ball of radius r. And I'm going to choose, I'm going to let n be less than this number, root r over 4 times the size of s. And I'm going to choose any cosets of infinite index, C1 up to Cn. So I'm going to imagine that somebody was able to, somebody saying, okay, take a look at these. I think that these cover your ball of radius r. So there's one here, and there's another one here. I have n of these. I want to prove that they don't cover the ball of radius r. So what I'm going to do is I'm going to calculate the probability that this Zr is inside the union. I'm going to ask what's the probability that I'm inside the union of these things. And I'm going to show that this is less than 1. Okay? And this will finish the proof, right? Because the probability is less than 1. In fact, with positive probability, I'm outside of these things, but I know that I'm in the ball of radius r. So I must be in this strange new land that is not covered by these things. Yeah? So in some sense, this is not unrelated to the probabilistic proof of the invariant measures that I mentioned before. All right. Okay, so how do we do this? Good. We're going to look at one of these CIs, and it's going to be something of the form HG. So we'll fix some CI which is equal to HG, where H is an infinite index subgroup, and G is HG is the coset. And what we want to figure out is what is the probability that Z is in this particular one. Now, if we show that that's really, really small, then that will imply that the probability of being in any one of them is also really, really small. We're just going to sum up all these probabilities, and by the union bound, so if the chance of being in any one of these is 1 in a million, and I only have 10 of them, then the chance of being in any one of them is at most 1 in 100,000. Okay. Now, okay, so what's the probability that Zn is in this HG? Well, it's the same as the probability that HZn is in HZ. Okay? Good. Now, the process, we're going to now look at the process Yn, so a sequence of random variables Yn, which are HZn. Okay, so Yn is now a random, so, and this should be R. Well, I'm going to leave it as, sorry, I'm mixing R and N here. Anyway, Yn is HZn. This is a coset. This is the coset of H that the random walk visits at time n. So Yn takes values in, now forget it right this time. H divides G, I guess. So it's a random process. And in fact, it's just the random walk on the Schreier graph. It's not exactly a simple random walk in the sense that all the probabilities are the same because, I've collapsed things. So maybe I have 2 generators taken to the same place, but it's still a Markov chain. Okay. So this is, and in fact, it's a symmetric Markov chain. In the sense the probability of going from one coset to another is the same as the probability of going back the other way. Okay, good. So what we want to do is we want to say the probability of being at any particular coset is small. But really all I know is that this is some kind of Markov chain. So I have the Schreier graph. I don't know what it looks like, and I have some probability of going from here to here, and then different probabilities of going to different places. I have some Markov chain on this Schreier graph, and what I want to say is I want to say the probability of being at any one particular place is low, but I really have zero control over the Schreier graph. If this is the free group, this could literally be any graph. Good. Yes, because it's because we're in the infinite index. Yes. I think maybe there's some other restrictions. Well, okay, you have to be able to label it with the generators and so on.
The only restriction is the degree of the vertices.
Is at most the size of the generating set. Okay. So this is about, we want some kind of very, very general bound on the probability of a Markov chain being anywhere. Okay, so let's try to understand whether such a bound can even exist. Let's take a super simple Markov chain, which is just the simple random walk on Z. So the Markov chain is now gonna start at 0 and just go with probability 1/2 to the left and with probability 1/2 to the right. And I want to ask, can we have some kind of lower bound that says that the probability of it being in any particular point is small at time n? So here, that's kind of easy. What do we know? We know everything you could possibly imagine about the simple random walk on Z. In particular, the place that's going to be, at least in even time, the place that we are most likely to be is back at 0. And the probability for this particular case, I'm gonna call it Ym, but this is a particular case. So the probability this Yn, okay, I'll write here Z, just remember, is equal to any k, is at most something like, I don't know, 13 over root n. Right? The central limit theorem tells us that this distribution is going to be more or less like a Gaussian with width root n. So the probability of being back at 0 is something like 1 over root n. And everywhere else, the probability is even smaller. So uniformly over all k, the probability of being at any k is at most 13 over root n. Okay. Now what we are wondering is whether something similar holds in general for infinite Markov chains. You can think of these Markov chains as graphs that you're only going to go to finitely many places from each place. And somehow it should be true because this Z is sort of the smallest infinite graph you can imagine. Anything else, well, maybe if you take the n, is the smallest infinite graph that you can imagine in the sense that it's a subgraph of any infinite graph. And in other graphs, I have sort of more places to go. So the probability that I'm back where I started and everywhere else should be even smaller just because I could have gone off in other directions. And this turns out to be true. So there's a theorem by, well, this, I'm gonna give credit to Lyons for this. This is a theorem by Russ Lyons from 2005. And I'm going to use, he proved something more general, and he's also building off of other people. I'm not going to mention the whole history of this theorem, but what he says is the following. Let W1, W2, and so on be a Markov chain on a countable set. It's called a set omega with symmetric transition probabilities. Denote by Q of omega 1, omega 2, the transition probabilities. Okay, so Q omega 1, omega 2 is the probability that if the Markov chain is at omega 1, at some time in the next time period, it would be at omega 2.
But I think you mean like this matrix.
Exactly. In fact, he needs something weaker, but well, this is good enough for us. I'm gonna let C, and I want to get this right, be the infimum over all these transition probabilities. Okay, where these transition probabilities from omega 1 to omega 2, where omega 1 is different than omega 2, and Q omega 1, omega 2 is not 0. So a lot of these transition probabilities are 0. I just want to take the lowest non-zero one. Okay, and then the probability that this Markov chain Wn is equal to some omega, any omega at all, is at most 4 over C times root n.
So I guess you kind of want these out of the infinite or something.
Yes.
Qualified, I think.
Yeah, so sorry. And I should also say an irreducible or ergodic, unaccountable, infinite. Yeah, so there are different versions of this, and maybe we could have used. Yeah, so I think he might have generalized it, and he might have generalized it beyond what we need. So maybe we were better off citing some earlier thing that wasn't quite as general, but was still good enough for us. Yeah.
It was the anti-concentration that was there already.
Sure. No, you're right. It says that, things are, it tells you things cannot be too concentrated somehow. They're spread out. Yeah. Okay, so now we're basically done. Obviously, these conditions are going to be satisfied by our Markov chain. Otherwise, I wouldn't have written them down. For pedagogical reasons, you can infer that these sufficient are satisfied. These conditions are satisfied. So what do we know? Oh, and our transition probabilities, since we took the uniform distribution on S, are just all 1 over S. All the non-zero ones are 1 over S. So what do we get? We get that the probability that that Zn, well, I get the probability that Zn is in this coset, which is the same as the probability that Hzn is in this, is equal to this coset, which is the same by definition as the probability that this Yn is equal to Hg, is at most 4 over root n times the size of the generating set. Now, if I have less, if I have less than 1 over this number, then by the union bound, the probability of being in their union is less than 1. So the probability that Zn is in the union of these CIs is less than 1 by the union bound. So that's the end of the proof. And the open question that I mentioned before is there a better lower bound? And that I don't know. And it's the same thing as asking what happens on the free group. Now, a natural question that we don't know the answer to, let's call it questions. What about the Grigorchuk group? What is this covering number of the Grigorchuk group? It's easy to show that it's at most R, but maybe it's less than R. We don't know. We don't know how to show that. And okay, for some reasons that I could explain, this feels like a natural candidate if there was going to be one.
If there was a big, like strictly less than our situation.
Yeah.
Like,
Yeah. So this is the best that we can do for a general group. What can we say about particular groups? So we already said something about ZD. And the proof for ZD can be extended to virtually nilpotent groups. But I'm going to, so for virtually nilpotent groups, the answer is also R. But let me show you a slightly more general statement. So here's a definition by Oechsler and Ozawa. I'm going to say that the measure group G mu, the random walk, the mu random walk on G is cautious if, so I'll write it as, the Zn is a mu random walk, Z is cautious if for all epsilon, the infimum over all times n of the probability that the random walk at time n is in the ball of radius epsilon root n of G with the, well, okay, doesn't matter, the ball of epsilon root n is greater than 0. Okay, what does that mean? There's some constant, say 0.1, so that I always have probability at least 0.1 of being inside the ball of radius 1/2 root n or 1/10 root n or whatever epsilon 10 root n. It basically means that the random walk hangs out with positive probability in the root n region. Okay, I'm going to say that G admits a cautious random walk if there is some symmetric mu finitely supported for which this holds. Okay, now here's the next result. And I'm calling it a theorem, but it's really it's the same theorem that we had before, just rephrased. If, okay, sorry, actually there's more to this. I take that back. If G admits a cautious random walk, then CR of G is equal to R. Yes, and is symmetric and finite. So yeah, so this means that U is non-degenerate and symmetric and finite support. Okay, so the theorem gives both directions. It says that it's equal to R. So we have to prove both sides of this. One side comes from Oechsler and Ozawa, and what they proved is that if you have a cautious random walk, and you have something called property FD. Correct me if I'm misrepresenting. Sorry, HFD. Sorry. How's it like this? HFD. Sorry. I'm not going to explain what this property is, but what then Shalom proves is that if you have this property HFD, then you have a quotient to Z. Okay. Oh, sorry. Quotient to Z of a finite index subgroup.
Amenable and
amenable and HFD. Okay, sorry for that. Okay, so, but like we said before, once you have a quotient to Z, you can pull that back up and you have that C is at most R. So you can always cover with R things. The question is, why can't you cover with less? Okay. And okay, I guess I should explain that any group that has this cautious random walk is going to be amenable. So we're in the amenable case. Okay, good. So this gives us one side. The other side, we're going to do more or less the same proof that we did before. But what we're going to do is, remember we had our group, and we had our we had our ball of radius R, and we did our random walk for our steps, and we showed that it doesn't intersect these cosets of infinite index. Now we're going to do a random walk for our squared steps. Now we're doing the random walk for our squared steps. It could in general be in the ball of radius R squared, but this tells us that, you know, we have some constant probability that it's in the ball of radius epsilon R at least. So again, up to constant, we're going to be within the ball of radius R. But now, because we did our square steps, the probability that this ZR squared is in one of these cosets of infinite index is going to be at most something like 1 over R. So I have a much lower probability of hitting any one of them because I've taken so many steps. So I'm going to need at least R of them to cover everything. So it's the same proof as we had before, except because we do this random walk for much longer, this theorem, which is not written down anymore, tells us that we're much less likely to hit these things. So we're gonna, even if we have a lot more of them, something like anything less than R, we're gonna have some gaps and not hit with positive probability. So I'm out of time. So you might wonder, you know, what kind of groups have this this cautious random walk? So the results due to Tessera and also to Tiani and Anna, that if you put them together implies it's actually a very large class of groups. It's virtually nilpotent groups, but it's also polycyclic groups, solvable Baumslag solitaire groups, lamplighter groups with finite lamps over Z, and more. Okay, so this is somehow a very large class of groups where we know that the answer is R. Okay, the last thing I want to tell you, and so I have until 12:20, is that right? Okay, so I have minus 20 seconds left. I'm good.
Using the plan.
So let me just state one more result, and with that I'll end. So here's the last theorem, which is that if G has property T for any finite symmetric generating set S, there exists some epsilon such that the number of cosets that you need to cover the ball of radius R is at least e to the epsilon R. So I need an exponentially many of these to cover the ball. And the proof of that is very simple. This epsilon just comes as some transformation of the Kashtan constant, and I'm not going to explain what property T is, but if you know, you could probably fill out the details of this proof in the next 3 minutes. So, but you look at the random walk on the Schreier graph, and actually the probabilities there decay exponentially quickly. So you do the same probabilistic argument, but now property T tells you the probability being in any particular place decays exponentially quick. Okay. Good. So we know that some groups are linear. We know that some groups are exponential. Is there anything else? Is there a group where C of R is R squared, R to the 17? We don't know. Okay. Is there anything where it's sublinear? We don't know. But we do know it's bigger than root R. Yeah.
In the last result, can you substitute property T
for having no amenable actions from the discrete set?
Yes, which is in fact known to not be the same
Yeah.
as property T. Exactly. So this, I forget there's a name of a property that implies that it's known to not be the same. I forget what it is exactly, but I think Yves Cornu has some results on that. Yeah, so all you need is that when you have okay, it's what Josh said. Yes. Yeah.
Are there any examples of amenable groups where it's more than R?
No, I only know about property T groups where it's more than that. So it could be, yeah.
If it's like an amenable group, we can't say that like it's maybe exponential, but depends in the generating set. Like, are there non-amenable groups for which this CR is sub-exponential?
I don't know. No. So for the free group, we know that it's at most R. So once you have a quotient to Z, you're at most R, right?
Okay.
So you'll need something that doesn't have now a very natural conjecture was maybe where Clinton's going is that for all amenable groups, this should be just R. And we spent a lot of time thinking about this, but somehow you get bogged down in really questions of how big do the Fellner sets need to be to get a surface to a volume.
When you say the thing, sort of this like growth rate, like the exponential growth rate, as soon as there's like a gap between like, I don't know, growth rates of normal subgroups.
This is not only about normal subgroups,
Yeah.
right? You could ask the same question for normal subgroups. I should say that I don't know that the answer is different for anything if you take normal subgroups. In fact, I don't know that the answer is different if you take all cosets of the same subgroup, right? Because
No, if you take all cosets of the same subgroup, there is this criterion for when the trier group, for when like the quotient subgroup. Okay, no, I guess it's different.
you might get the same answer as you did if you allowed different subgroups.
For a particular group, use normal subgroups, the answer will change a lot. Yeah. Groups don't always have interesting normal subgroups. There are simple groups.
No, okay, yes, I see. That's a good one.
Problem to your explanation.
Yeah, I guess you have a simple group, then you get a very direct answer for normal subgroups. Yes.
So what happens to your group if you use the sphere instead of the ball for it? For the three groups, your estimate for three groups. Do you get the same estimate on your?
I have not thought about that at all,
I
actually.
mean,
So I don't know.
how could it be different? Because like in the free group, like half the ball is here, right?
Yeah, so yeah, I'm guessing at least one direction is going to be immediate, and I don't know about the other.
With the temper,
could
one
probably
with
take
the
I see, yeah, okay.
Is there any candidate, like from regards to group, you're saying if there is below sublinear, then this is the candidate, maybe.
Maybe.
Is there any candidate for like anything that's not exponential, between exponential and the?
Okay, that's a good question. I don't know. Yeah, I guess one thing I can say is that if you allow for not normal subgroups, but if you want all these cosets to be the cosets of the same subgroup, we again don't have any different results.
And all techniques work for that too, right? You're estimating probabilities in a triograph of a particular group subgroup. So doesn't your proof go through?
So okay, so if you have one subgroup, then its triograph is going to be infinite, which means that you can always do it with you always need at least R to cover.
Right.
So you're not going to be able to do it with less than R. But we don't know if there's any group for which this covering function is going to have different asymptotics, because we don't know if there is anything that's less than R. Yeah.
Does your thing work if instead of like taking, Cayley graph with word metric, you have a group which acts like compactly and something, then you take coming from the orbit space, like like you act and quaternionic hyperbolic space or something, like a lattice and that is property T.
I have not thought of that. Okay, but I'm hoping
So
you.
maybe
I'm hoping you will.
random walk to use like Brownian motion or something. I mean, yeah, instead of this.
But it's-
Yeah.
What about products of Cartan groups? Does the products make it, can it make itself a two-dimensional? Like.
That's a nice idea. I haven't thought of it. Yeah, so the question is, are you going to get in this product subgroups that have that don't have this exponential decay property? Somebody should know the answer to that. Maybe somebody here. Yeah, I don't know.
It's also time to organize for this field.
Yeah, I personally think Martin, Nico Schaber, and Danny Weiss for most, like Danny Weiss, especially for doing most of the work. Trust me, you see maybe me walking around talking, but the most of the work is there.
I mean, I didn't want any of these people to speak.
Okay.
Here's an important announcement from people with power. They want keys. I don't know how I do it, but I'm told by someone competent that there's a mailbox somewhere on the fifth floor.
There is knowledge on of the mailbox where it is, so we can
Great.
maybe.
That's
maybe
maybe
contact.
keys. There are going to be people here in the future, and we want them to have keys to their offices.
Okay, so ask Conrad where the mailbox is.
You don't give your key back.